Okay, so let me go back to that. Okay, so here is, where'd it go? There we go. Okay, so here it is. So in parallel, out through the focal point. So I just put my ruler right there and I draw a straight line out through the focal point, and I just draw it however long it needs to be drawn. Then in through the focal point, so I take my ruler from my object, I draw it through my near focal point. When it hits the center of the lens, it goes out parallel. These two rays that left the top of this object right here come back together right here. So that's where my image forms. My image, the top of my image will be here. Its feet will still be on the optical axis, so its feet are still right here. So my image is upside down. So the top of my image is here, my feet are right here. So my image is upside down. Now, because these light rays actually cross, that's a real image. So there's my first criteria, it's a real image. Okay, the second criteria, is it upright or inverted compared to the object? So this object is this way, my image is this way, so that's an inverted object. And in this case, it is clearly smaller than my object, smaller, so we say it's reduced. That's my third criteria. Can't catch my pinky. That's my third criteria. So it's real, inverted, reduced. Okay, that's the three criteria for that image. So in parallel, out through the focal point, in through the focal point, out parallel. Okay, all right. Now, if anybody's got questions, just jump in and ask. Okay, don't sit there and be confused. Now, the next one, I'm going to have the same kind of lens. It's still a positive lens, but now I have moved my object to where now it's between the radius of curvature and the focal point. All I've done is move it. I'm going to use the same two rays, in parallel, out through the focal point, in through the focal point, out parallel. And I messed up there and didn't use my red pen, but I kind of tried to draw over the top of it so you could see. So in parallel, the optical axis, it's going to refract out through the focal point. Okay. Then in through the near focal point, out parallel. So this is where they come together. So they actually come together. So it's a real image, right? The light rays actually cross. It's upside down compared to my object, so it's inverted. But now it's clearly larger than the object, so we say it's enlarged. It's an enlarged object. Okay? So the three criteria for that would be real, inverted, enlarged. Okay, real, inverted, and enlarged image. Now, anytime you have a lens like this, a convex lens, and you get between the radius of curvature and the focal point, you're always going to have an enlarged image. If you're outside the focal point, you will, or excuse me, outside the radius of curvature, it'll always be a real, inverted, reduced image. If you're between the radius of curvature and the focal point, it's always going to be a real, inverted, enlarged image. Okay? But remember I said I don't like calling them, because this is converging. These light rays are actually coming together here to form the image. Remember I said I don't like calling them converging lenses, because you can force this situation to become diverging. And that is when you put your image or put your object between the focal point and the lens. So you're inside the focal point. So here's my object, in parallel, out through the focal point, just like before. But now in through the focal point's a little trickier, because the focal point's actually back here. So I have to put my ruler on this arrow and line it up to say, okay, like this red ray looks like it came from the direction of the focal point, but then it's going to go out parallel. So now the problem is these two light rays right here are never ever going to cross, are they? They can't cross. So what I have to do is I have to project them back. So that's what these dashed lines are, is me projecting these light rays back, like that. And then they look like they cross right here. So they don't really cross. They only appear to cross, okay? That's where my brain, if I were looking with my eyeball through this lens, this is what I would see. I would see this image like this. So that is a light, those light rays don't actually cross, so that's a virtual image. So that image is virtual. It has the same orientation as the object, so it's upright, and it's enlarged. So virtual, upright, enlarged. That, my friends, is a magnifying glass. Because if your eyeball is over here on this side looking in, you hold the magnifying glass over whatever it is you're trying to look at that's small, and you want to make it bigger. But you want to see it in the glass, you want it to be enlarged, and you want it to be the same orientation as the object, right? So that's a magnifying glass. Okay, so in that case, that positive lens or that converging lens has been forced to become diverging because of where I've put the object. So anytime I have a converging system, if I put the object inside the focal length, it will become diverging and I will form a virtual image. Okay? All right, now the other kind of lens is a biconcave lens. So that's what this thing looks like. So notice it caves in here, thinner in the middle than it is at the edges. Now, in this one, it's a lot easier. It doesn't matter where you put the object. There's only one kind of image you're going to get because it's always going to be a diverging system. The only kind of image that you're going to get is a virtual, upright, reduced image. How much it's reduced depends on where you put the object, but it will always be virtual, upright, and reduced. Okay, so the way that works is the same as before, in parallel, out through the far focal point. Well, now because this lens, the back side of this lens, or excuse me, because the far focal point is determined by the front side, because it caves in, its focal point's over here now. So that's my far focal point. Flips, all right? So I have to take my ruler because this is going to diverge. It looks like it's trying to come from right here. So I take my ruler and I draw it along that line. So that automatically spreads the light out. Then in through the near focal point, well, the near focal point is determined by the back side of the lens, which is this side. Its focal point's over here. So this light ray is trying to go toward that, but it's going to hit the lens first and it's going to come out parallel. So it's still in parallel, out through the focal point, in through the focal point, out parallel, but it looks a little weird because this is a concave lens. The focal point's reverse. So these two light rays over here will never ever cross. So I have to track them back or project them back, and this is where they look like they cross. So again, they don't really cross, so that is a virtual, upright, but reduced image. So that's something called a reducing glass. Okay, a reducing glass makes the things, it works just like a magnifying glass, but in the opposite way. It does the same thing, but it gives me a reduced image. Okay, okay. Any questions about that? No? Okay. All right, now, with lenses, the light goes through them, okay? The outgoing rays are always on the other side from your object, but with mirrors, the outgoing rays are always going to be on the same side as your object. So we're going to look at ray tracing for mirrors, okay? So I'm going to start with a concave, or what they call a converging mirror, with a positive focal length. So the object in this case is outside the radius of curvature. So just like we got before, we got a real inverted reduced image, but this time it's still in parallel out through the focal point. So the mirrors luckily only have one focal point. That makes it easy. So in parallel out through the focal point, then in through the focal point and out parallel. Now you may say, but Dr. Burris, those two light rays cross there. Well, one's an incoming ray and the other one's a reflected ray, so they don't make an image. That's why. Okay, notice they reflect. They come back on this side. The light can't go back here because that's the silvered part of the mirror. You can't put light back there. So it has to bounce back from the direction that it came. So in parallel, out through the focal point, in through the focal point, out parallel, and then this is where they appear to, or where they actually cross. So that's a real image. It's upside down, so we say it's an inverted. It's upside down compared to the object, so we say it's inverted, and it's reduced. It's smaller. Okay. All right. So that's kind of like what we got with the lens for a different reason, but it's the same style of image. Okay. Then we're going to move it in between F and C. And just like we saw before, it gave us a real inverted enlarged image. So in parallel, out through the focal point, in through the focal point, out parallel, and that's where they cross. So it's actual crossing, so it's real. It's inverted and it's enlarged. It's larger than my object. So that's the same thing as we got with the lens, again, for different reasons, but it's the same thing. But guess what? As you might have already figured out, if we get inside the focal point, now we become diverging. So in parallel, out through the focal point, in through the focal point, I have to dash back with my ruler, and then it looks like it came from this way, so it comes out parallel. Well, again, they don't really cross, so my brain projects them back, projects those outgoing rays back, and they look like they cross here. Now we know the light's not really back there, so that's a virtual upright enlarged image. That is a magnifying mirror, like a makeup mirror or a shaving mirror. If you've ever used one, you'll notice they curve in a little bit. And the other thing that you'll notice is you have to be close enough to them or they don't work. If you've got them sitting across the room and you try to look at them, you're not going to see an image in the mirror because that mirror is actually forming a real image, you know, somewhere out in space. You can't really see it because the light's not strong enough, but it's not working as a mirror, as a makeup mirror yet, because you have to get close enough to it. You have to get inside its focal length for it to work as a magnifying mirror. Okay. Now, that's a concave, in other words, it caves in mirror. Now, convex mirrors are your diverging mirrors, or they bow out. Okay. So they will do the same thing as the diverging lens. They will always form a virtual reduced upright image for the same reasons. Okay. In parallel, out through the focal point. So I had to take my ruler and track it back. In toward the focal point, it comes out parallel. So I take my ruler and track it back. There's my little bitty image. Now, these kind of mirrors form a virtual reduced upright image. You have one of these probably on the passenger side of your car's rear view mirror that says objects in mirror are closer than they appear. What those do is they give you a smaller object, but they give you a bigger field of view. So that way you can see when you're passing somebody, you can see in your blind spot. Or if you pull a trailer, you have a trailering mirrors that you can buy, the little round stick-on mirrors, or sometimes trucks or towing vehicles will come with the bottom mirrors that are the towing mirrors so you can see around the blind spot. Or security mirrors in convenience stores, or sometimes they'll have them in restaurants coming out of the kitchen if there's a blind corner. You can't, that way you can see around the corner. Everything looks smaller, but you have a bigger field of view so you can see in those blind areas, say around a corner or at the end of an aisle where you can't see if you're at the front of the store. So that's what those are. Okay. Okay. So I'm going to stop the recording.